Hi, my name is Andrea Gaucher, and I'm in the group of Luan Chalder and Celia Saï. Our case, we choose to work on the case drug expenditure in France. So, um, so our contact is gonna be organized in four part. The first part is the introduction of the model. The second is a presentation of the model, the presentation of the code, and finally the conclusion. So, our case is understanding drug expenditures in France. So, there is some key numbers of our case, but let me introduce a little bit more about the national context. So, in France, healthcare is a cornerstone of public policy. Each year, more than 250 billion is spent on health, and approximately 35 billion of that goes toward reimbursed medication. With an aging population, a rise in chronic illness, and the arrival of expensive innovation treatments, the national healthcare system is under pressure to manage spending efficiently while ensuring equal access to treatment. However, medication-related expenditure varies significantly depending on factors like region, prescription habits, and patient demographics. Understanding these patterns is essential to reduce unnecessary cost and to design better health policy. Um, as a personal trigger and project objective, I asked myself a simple question. As example, I put it in my diapositive. Every year, I see my parents spending quite a lot on medication. That made me wonder why, which drugs cost the national health insurance the most, and more importantly, do costs vary depending on the patient's sex or where they live? For instance, can we anticipate the reimbursed amount based on a simple variable like sex and region? The challenge is that the available data is massive and complex with thousands of rows and technical identifiers like drug codes, ATC classification, etc. And extracting meaning from this is really difficult without the right analytical approach. So our project objective is not only to analyze existing drugs expenditure patterns, but also to take it a step further. I aim to build a predictive model that can estimate the reimbursed amount for a drug based on a patient's sex and region. This predictive approach could help to identify region or population profile where drug spending is unusually high, support healthcare policy maker in forecasting cost, and finally, improve regional or demographic equity in access to care. Why it matters? Turning raw health data into a predictive model means giving public institution a decision-making tool that is both proactive and data-driven. Instead of just reacting to overspending, we can anticipate it. We move from information to actionable insight. And finally, this promotes transparency, efficiency, and more balanced public health system across the country.
In our working context, we'll be exploring two different models. First, let me introduce you to a powerful yet simple statistical tool, linear regression. The linear regression predicts numerical values like price, temperature, or scores, based on one or more input variables. Imagine being able to predict a property value just by knowing its square footage, a vehicle fuel consumption based on its speed, future product sale using marketing budget data. Imagine in a practical scenario. Picture yourself as a real estate agent. You intuitively know a 150 square meter house sells for more than 30 square meter house studio. Linear regression turns this intuition into a precise mathematical equation. The core idea is finding the best fitting straight line through your data point using the least squares method to minimize errors. This is the formula. This is a simple formula. We have the target variable, the predictor variable like the size, the slope, and here the intercept. Concretely, if ours costs 1,000 euros per square meter hours with a 50,000 based price. This is the formula for find the final price for 130,000 euros for an 80 square meter house. Now, let's turn our second model, a true technological revolution, deep learning. This technology has completely transformed the artificial intelligence landscape. Deep learning enables machines to learn complex patterns directly from data without explicit programming. Some groundbreaking applications imagine recognition like Facebook or smartphone identifying friend in your picture. Self-driving car that see pedestrian and traffic sign. The voice assistant like Siri or Alexa understanding natural languages. And in medical, when AI system detecting invisible anomaly like from X-ray. Deep learning mimics the human brain. Through artificial neural network, unlike linear regression with its simple equation, deep learning uses thousands of neatest formulas. K connector visualizate each neuron equal a smart mini calculator. Each connection equal an information filter, and each layers equal a refining sieve. Here we have the formula of the deep learning. With the input for the X, the waste for the W, the BIs, like in the linear regression, and the activation, like a function, adds non-linearity. In the real context, with the deep learning, we can recognize a cat in a picture, step by step. First layers detected age, the second layer identifies the eyes and the ears, and the deep layers recognize the Persian cat. In our project, we will use linear regression to analyze the relationship between gender and reimbursable amount, the relationship between the region with while the medication are purchased and reimbursable amount. Then we will use deep learning to understand how the reimbursable amount is influenced by the combined effect of the two variables, gender plus purchase region.
So now I'm going to introduce you to the code we run to interpret our result. At the moment, we modify it by deleting and adding lines of code to be able to interpret it. And I just run it right now. So I'm going to show the line to say what it is about. So this first line of code imports several Python libraries that are used in data analysis, modeling, and machine learning. It is therefore necessary to build, train, and evaluate predictive models. Just right here, we import our 3 files that contain our data. Then here we can see the number of rows and columns of our respective files following years and after. We have a sample to be able to view it. At this stage, we add a year variable that will give us the year for each of our 3 files. Here, we ask to show us the name of file columns. And in this part, we can see that there are differences of name between different variables, which are the age, the LCIP13, and the same with a lowercase l. So we make sure that these lines of code, with this line of code, we make sure to have the same columns names for our files so that we can concatenate them just here. Then we ask to have the shape of our file, and then we ask to show it. So here we can we want to check for we can see it here. Then we wanted to check for each variable the percentage of missing values, and we can see that we have no missing values, so we can go to the next step. So in our data analysis, we will focus on only some of the following columns. So the sex, the region, and the BSE, which is the repayment basis. So the notebook offered us to transform the variable sex just here, which is represented by numbers by associating the number 1 to the word masculine, the number 2 with the word feminine, and the number 9 with the word unknown. But as a part of our analysis, we decided to leave the variable as it is. So just right here. We have done the same with the region. And here is a sample of our final database with our 3 variables. So to remember, these are the columns we need. And the line of code after, clean the BSE column by removing spaces, filtering valid values, removing unnecessary point that define 1,000, replacing commas with point that represented decimals, and finally converted it to a numeric type, which is float, because initially these numbers were in object type. And as my colleagues have said, we choose to analyze our data with the method of linear regression and deep learning that we can create it here. Yes, just here. And the objective was to predict. So as we show it in class, the step here allows us to divide the data into 2 sets. So the training set to learn the model that use 80% of the data, and the test set to evaluate the performance of the model once it has been trained, that use 20% of the data. Then this line allows to train the linear regression model by learning the relationship between the variable sex and the BSE, the variable BSE. Then it is now a question of analyzing the results of this regression with a particular 3 indicators, which are MSE, the coefficient, and the intercept. And the linear regression model shows us an inverse relationship between the the sex, and BSE, with a female gender having a lower predicted value of BSE compared to men. However, the high MSE indicates that the model may not be adapted or fully capture trends in the data. It is likely that additional variables or a more complex model would be needed to better predict the BSE target variable with greater accuracy. So here we decided to plot our linear regression using a graph. And this chart suggests that the repayment basis is generally low with some significant variation and outliers. The trend indicates a possible slight difference between the sex, but further analysis will be needed to confirm this observation. And we did the same with the region. And then we have used here the deep learning model. And it took us approximately 4.5 hours to finish the analysis. So we had made some screenshots to show it. So this was the step that took us a lot of time. So to go to the conclusion, we obtain this graph who is to the right, and by interpreting it, it tells us that our model doesn't generalize well the new data. There is probably a problem in the normalization architecture or the training But a few days before we ran the model, and we had another graph that looks like the one who is to the right up hand. And the conclusion we were able to make was that there was a slight correlation between the variable sex and the variable region as a function of repayment amount, so the BSE, hence the fact that the curve becomes linear. So in the end, we couldn't come to a single conclusion. And also we found another problem because at the beginning, we would like to add the age to analyze our data, but the code had made some groups too large to exploit them by a range of 0 to 19, 20 to 16, etc. So it was too complicated to interpret something. So this is the end of our project, and thank you for listening.